Okay, so now we look at this notion of weak ties and strong ties. So we will classify an edge as a weak tie or strong tie based on its neighborhood overlap score. So if the neighborhood overlap score for an edge is less than or equal to a threshold, then that edge can be called a weak tie, otherwise it is a strong tie. So what is the threshold no score? Okay, that's what you're going to determine as through an algorithm. But as of now, let us say you're given a threshold no score, then if the no score for an edge is less than or equal to this threshold, then that edge can be called a weak tie. If the no score of the edge is above this threshold, then the edge will be called a strong tie. So we saw earlier that the edges with lower no scores will serve as a bridge between two different communities. As you saw, the end vertices of these edges will have few common neighbors. If edges have a larger no score, we also saw that those edges will be well within a community, as the end vertices of these edges will have more common neighbors. Okay. So now we previously saw this Girvan-Newman algorithm, which is a very uh, it's an optimal algorithm in the sense that it gives you a very good modular communities, but it goes through a sequence of iterations. So now we'll look at a simple community detection algorithm based on this notion of weak ties and strong ties. So we'll use a binary search approach to identify that minimum threshold no score. And now, what is that minimum threshold no score? It should be a no score that will make the graph to satisfy the strong triadic closure property. Now, what is the strong triadic closure property? This is the property. If a node has strong ties with two of its neighbors, okay, so let us say there's a node A, it has a strong tie with two of its neighbors B and C, then we expect B and C to have at least an edge between them. That edge could be a weak tie or a strong tie, but at least B and C should have an edge between them. So if a node has strong ties with two of its neighbors, then the two neighbors should be connected to each other. That's basically what it is. So if a node satisfies this property for any two of its strong tie neighbors, then that node is said to satisfy the strong triadic closure property. If every node in the graph satisfies a strong triadic closure property, then the whole graph is said to be satisfying the strong triadic closure property. If even one node does not satisfy the property, which we say is violating the property, then the whole graph is considered to violate the property. Okay. Um, so, for example, in this graph, these are the no scores of the edges, and let us say the threshold no score is 0.4, then all edges whose no score is less than or equal to 0.4 will be called a weak tie. So for example, 5,9 has a no score of 0.33, so this is called a weak tie based on this threshold of 0.4. Whereas say 1,5 has no score of 0.75, and based on this threshold of 0.4, this is called a strong tie. So once we classify the edges as weak ties or strong ties, then we go through every node and check for any two of its strong tie neighbors, they have at least an edge between them. Okay. Um, so what we then do is, so continuing the same example, once we have classified the weak ties and strong ties and made sure the strong triadic closure property is satisfied, we will simply remove all the weak ties and let the graph to disintegrate into communities or clusters like this. So these are now the communities that we have, and that's one step process. So the modularity of this community 1356 is 3.02. The modularity score for 478 is 2.24. So we get that through the pairwise modularity scores. And the modularity scores for 2 and 9, they are individually on their own community, is 0. So the total modularity score is just the sum of these two, which is 5.26. Okay. Now, if you compare this with the Girman-Newman approach, it may not be as efficient as this, because the Girman-Newman approach gave us like what, 7.34. It partitions the network into 13569 and 2478 as the most modular communities, and the modularity score in total is 7.34, which is more than what we got here with 5.26. But you see the time. So this weak time space community detection is going to be more time efficient. Okay, it may not give you optimal or more modular communities, but it is more time efficient. Okay, so let us go through this binary search algorithm in another video.